Hello, everybody. All right, so hopefully at this point you're pretty good on strong acids and strong bases and how they work and how they act and all that sorts of stuff. I want to just start with a quick review here, and we'll get into our problems today. We're going to talk about weak acid, weak base equilibrium problems, kind of an extension of the last unit. But remember, pH is the negative log of the concentration of H plus. pH plus pOH equals 14. That's the derivation of that H plus times pOH concentration equaling Kw. Any weak acid is going to have this equilibrium expression. Again, products, concentration of the products over the concentration of reactants. Your H plus is the important one. That's going to be able to be used to calculate your pH. And I want to highlight Kb. It's often neglected. I'm going to neglect it today. But Kb is the same thing. Products, concentration of the products over the concentration of the reactants. It has this form of OH minus Hb plus and B. What is going on there? So I gave you an example. All right, if we have NH3 in water, it's going to dissociate into NH4 plus and OH minus. So again, you're going to have an anion and a cation. OH minus is going to be your concentration. That's going to give you your pOH, or you could calculate that using your Kw equation and get H plus, then do the P negative log. Then you're going to have NH4. All right, you're going to have that extra hydrogen on there. And then B is your base. You may be thinking, hopefully you already know the answer to this, but what about water over here? Well, water is a pure liquid. And remember, we eliminate any pure liquids from our equilibrium expression. So with that, let us begin with, I'm going to get rid of some of this stuff over here, I think. So I'm actually going to get rid of this. So we have this problem. What is the pH of a 0.0037 molar solution of carbonic acid? And here's our equation. We have, what's going on with that guy? Come on, go away. Go away. Come on. H2CO3 aqueous is going to dissociate H plus and HCO3 minus. First thing we're going to do is write that equilibrium expression. All right, so we're going to have Ka equals the concentration of H plus times the concentration of HCO3 minus. Oh man, my handwriting's taking a hit today. Times all over. Sorry, the acid H2CO3. And give me a second here. Hey, where'd that come from? K is 4.3 times 10 to the minus 7. Remember the Ka, like any K, is the measure of products and reactants and their favorability. But with acids, the lower the number, the weaker the acid. The larger this number, the greater the acid. And this is a pretty weak acid at 10 to the minus 7. So that's your Ka is 4.3 times 10 to the minus 7. All right, so we have this, and what we're going to have to do, since this is an equilibrium, all right, and a weak acid, it's not going to be 100%. And we have some idea of the 4.3 times 10 to the minus 7 over here, but it's not, it's not clear exactly what's going to be what. So this is where you do your ice chart. I mentioned this like last unit. These tend to be a little bit easier because there's a shortcut. And what I like to do is set it up over the equation. All right, I is initial, C is change, E is equilibrium. So initially I have 0.003. What is going on with this thing? It's driving me nuts. 0.037 molar. And initially I have 0 H plus and 0 OH or HCO3 minus. We can draw little columns if you want. Yeah, there we go. The change, all right, it's a 1-to-1 ratio across the board. So my acid's going to lose X. My products are going to gain X. Nice and easy. And then at equilibrium, it's going to be 0.0037 minus X. And then both of these will be X. And now, once I have this, I can substitute this back into my equation. So I end up with 4.3 times 10 to the minus 7 equals H plus, which is an X, times HCO3 minus, which is another X, all over the acid, which is 0.0037 minus X. Now here's where it's tricky. Before we're doing this and you end up with these equations, you end up having to use the quadratic formula, and it gets kind of messy and it's not time consuming. But if you take my word for it on these equilibrium acid problems and weak acids and bases, this X here, when I subtract it from 0.0037, actually won't change the number. It's so small that it's not going to affect this number. So we could just drop this. All right. It's negligible. Hold on, buddy. Sorry, my son wants me to change the channel or something. So I drop this. That goes out. So now I take 0.0037 multiplied by both sides. Hold on a second. I got to take care of them. So when we multiply both sides by 0.037, we end up with 2.0 times 10 to the 9, I believe it's minus 9, equals x squared. You get x, you take the square root of both sides, and you end up with, round it up, 4.0 times 10 to the minus 5th. Oops, I'm getting kind of sloppy here. Times 10 to the minus 5th. And this is going to be your concentration of H plus, right, which is also your concentration of HCO3 minus. But remember, we're looking for the pH. So we have the concentration of H plus, and to get the pH, you take the negative log, and you end up with a pH of 4.40, which is a good weak acid. Now, the other thing you can do with this is get your percent ionization. Right, so I have this number here. Right, this is my concentration of H plus. Right, so it's 4 times 10 to the minus 5. That's my concentration over my original concentration, which is 0.0037. Right, and that'll give me my the percent ionization, which you can be asked for sometimes as well. And this ends up being a 1.1% ionization. All of these acid-base problems work very similar, and you can do the same concept with weak acids, with weak bases in the Kb, and you can solve for OH minus and then use the OH minus to then substitute in and find the H plus. Do be careful of dissociations that are not one-to-one. Off the top of my head, I can't think of any that are like that for weak acids. Another thing to note is this acid is a polyprotic acid, so it's going to dissociate, and that'll be your initial K. Let me do this real quick. Let me get rid of this. Yep. Let's try to erase. Let's look at this. Look at that. Look at that. That's pretty cool. So you have that. This is your Ka. This would be Ka1. Alright, and then this guy, this product, is also a weak acid. It's got that H that can donate. So you're going to have a second protonization, which you could end up with. And you'll end up with H plus and CO3 2 minus. And this equation, you could set it up in equilibrium, would be a Ka and it'd be a second one. So you'll see that sometimes. But unless specified, don't worry about the second or third protonation if it's a multi-hydrogenated substance. We're usually just focused on the first K, whatever the question's asking for. To recap, right, you have your initial concentration, right? The products will be at 0. You subtract X, it's probably going to be 1-to-1. If not, you can sneak a 2 in there if needed, and then you combine them. Put them into the equation. The big thing to remember with these acid and base problems is that this initial acid or base, when you're subtracting it out, it's usually small enough to be negligible, so you can just drop it. I don't know that the College Board's ever asked you not to do it. Do the quadratic formula. If they do, that's on them. But But again, if you want to double check, you can look at this number 4 times 10 to the minus 5. I'm subtracting it from 0.0037. It's still going to be right. I mean, you'd round up to 0.0037. All right. Good luck with the problems. Tomorrow we're going to talk about buffers and calculating buffers. And it's going to be a lot of fun. More fun, or as much fun as today, I guarantee it. I still need lots of subscribers in order to monetize this channel. Need to be rolling that money, so subscribe and just keep watching it on repeat. And enjoy your day.